Sitting far away is not a good idea. Alright, so there's a lot of good problems on the midterm. So one of your homework problems is to look at the exam, look at the solution key, and then redo any problem you had, say, lost at least 10 points on. If you have not lost at least 10 points on any problem, obviously you do not need to do that. There are two ways to interpret the last problem. Either way is fine. They'll give you slightly different answers, and I only included one of them in the solution key, but I will send a little email note about how you would do the other one. What I want to do today is talk a little bit about the CDF method, and then talk about how you solve one of the biggest issues in Calc 2. So what's the big problem in Calc 2? What's the big lie or the false impression you've received from Calc 2?
That you can integrate most things.
That you can integrate most things. So what I want to do today is I want to show how using probability we can actually get around the fact that for the most part we don't know how to integrate. And this is actually very useful. A lot of modern finance and a lot of economics, a lot of applications are based on the ability to numerically approximate 360-dimensional integrals very quickly. So this is called Monte Carlo integration. Very recently, one of my former students was at a job interview, and he was given a question on Monte Carlo integration, and he was able to answer it in an intelligent manner. So this is something that could show up on some of those job interviews. Right. So the CDF method is a powerful way to create or to find the probability density of a random variable that's related to another random variable. So, have you seen any probability? Okay, have you seen random variables? No. Okay, so we'll just say a quick review. So x is a random variable if the following two things hold. One, we'll do a continuous density function f of x satisfies f of x is greater than or equal to 0, so it is never negative. And 2, the integral from minus infinity to infinity of fx of x dx equals 1. So we could think about maybe the probability that you will come to Williams. It is definitely not negative, and we know it's clearly not going to be more than 1. If you want to find the probability a less than or equal to x less than or equal to b, this would just be the integral from a to b of fx of x dx. Here's a, here's b. And in fact, this is why we care about integration, or at least this is one of the reasons we care about integration. Integration allows us to calculate probabilities. We, for the most part, don't really care about just areas of regions, but the probability that an event happens, that's useful. So, given a PDF little f of x, its CDF, or cumulative distribution function, big f of x, would just be the integral from minus infinity to x of fx of t dt. So as we go down to minus infinity, this goes to 0. As we go up to positive infinity, it goes up to 1. And the important thing is, by calculus, if we know the cumulative distribution function, we can recover the probability distribution function just by differentiating. Now there may be a couple of points where the PDF is discontinuous. The nice thing is the CDF will be continuous, and it will be much nicer and much easier to work with. So when you're doing arguments like this, in the back of your mind, whenever you see notation, you want to think, why are we choosing to use this notation? Well, big F should make us think of an integral. So let's do an example. Let's let x have density, I think I chose 1/2, yes. 1/2 if 0 less than or equal to x less than or equal to 2, 0 otherwise. So I'm choosing a uniform random variable from 0 to 2, and I'm going to let y equal x squared. And so what I want to do is I want to calculate what is the density of y given that I know the density of x. So without actually calculating it, does this seem like a calculation we should be able to do? Should we be able to understand y from knowing x? Alright, so the way I like to do these problems is the CDF of y. So let's calculate the probability that big Y is at most little y. And we know big Y is just x squared, so this is the same as calculating what's the probability that x squared is less than or equal to y. Alright? Can somebody give me another way of writing the probability that x squared is less than or equal to y in a more useful way? What's a more useful way of writing the probability x squared is less than or equal to y? Yes?
Probability x is less than 3 to the square root of 1.
You're correct in this case, but you might not be correct in general. You are correct, but you're correct because of something special about this density.
Also greater than or equal to the negative.
Also greater than or equal to negative square root of y. Okay. So I deliberately chose the problem so that if I forgot to mention this in class, we would not get the wrong answer. But you have to be careful. When I talk about x squared is less than or equal to y, x squared less than or equal to y, if and only if negative square root of y less than or equal to x less than or equal to square root of y. Well, for our problem, what's the probability x is less than 0? It's 0. So we don't have to worry about that in this case. We just get, this is the probability that x is less than or equal to square root of y. Okay? Can we calculate the probability that x is less than or equal to square root of y? I have the PDF. Can I integrate and find the CDF? Sure. Big Fx of x is the integral from minus infinity to x of f of x of t dt, which will be the integral from 0 to x of 1/2 dt if 0 less than or equal to x less than or equal to 2. Is this a hard integral to do? No, right? But do we need to actually do this integral? We're trying to find the probability density function of y. How do you find the probability density function of y? How do I get my hands on the probability density function of y?
Is that a capital F on the left?
That is a capital F. So how would I get to the probability density function of big Y? Yeah?
You just plug in root y for x?
For which?
I mean, in the...
For here?
Yeah.
So that's one thing I could do, but that would require me to actually evaluate the integral. That would give me the CDF. Right. So once I have the CDF for y, how do I get the PDF? Differentiate. Okay, so let's think about what we're going to do. We're going to integrate, and then we're going to take the derivative. Who thinks this is a good idea? What's going to happen if you integrate and then immediately differentiate? I'm sorry?
Look at the function.
Yeah, you return to the function you have. When you integrate, you might change this, choices, can add a constant c, but when you differentiate, it doesn't matter. If you integrate and then immediately differentiate, you return to where you started. Is there any reason for me to write down what the what the CDF is here? No, I'm going to differentiate on the next term. So let's just do it formally. It's big Fx of square root of y. And this will be big Fy of y. The cumulative distribution function of y being at most y is the cumulative distribution function of x evaluated square root of y. Okay? So again, I could write down the CDF explicitly. This is not a hard integral to do. We'll just get, I think, x halves, so we get square root of y over 2. But I want to avoid doing that. All right, now, how would I take the derivative of this? What do I have to use? Chain rule. So I'm going to write it very slowly. d by dy of Fy of y is going to be the PDF of y. And now when I take the derivative of this by the chain rule, I get the derivative here, evaluated square root of y, times the derivative with respect to y of square root of y. Now, the derivative of the integral of little f of x is just little f of x. So we just get fx of square root of y, and now we have the derivative of square root of y. That's y to the half, so it's going to become 1/2 y to the minus a half. Okay? What is fx of square root of y equal to? So we have it's equal to what? So looking up here, it's just 1/2. So we get fy of y is 1/4 square roots of y. What's my range for y? What's the range for little y?
0 to 4.
0 to 4. And 0 otherwise. Okay. Whenever you get an answer, you should do some sanity checks. Can anybody think of any sanity checks we can do here? This is almost more important than finding this density. I don't really care about this density. What can we do to see if this is reasonable?
Should integrate to 1 and be positive.
Should integrate a little bit weaker than positive.
Non-negative.
Non-negative. So it's non-negative. That's fine. Now we need to check, does it integrate to 1? So check. The integral from 0 to 4 of 1/4, I'm going to write it as y to the minus a half, y is 1/4 y to the 1/2 divided by 1/2 at 0 and 4. 4 to the 1/2 is 2. 2 divided by 1/2 is 4, times 1/4 is 1. Okay, it does integrate to 1. Does anything look strange about this density function? So it's non-negative, which is good. It integrates to 1, which is good. But something should bother you a little bit about this. Or you're far more tolerant than I am.
It's undefined at 0.
I'm sorry, it's undefined at 0. The density function blows up at 0. Is that a problem? Well, fortunately, it doesn't blow up badly. It blows up like 1/square root of y, which is still integrable. And so if I want to calculate what's the probability between 0 and 1/1000th, I can still do that integration. It's fine that it's blowing up at the origin because it's not blowing up too rapidly. If it was y to the minus 3/2, that would be different. Or if it was 1/y, that would be different. It's blowing up at an acceptable rate. So I find this problem a little bit surprising. You take a really nice random variable, it's uniform from 0 to 2, you square it, but the resulting density function has a blow up. Okay? So it's an okay blow up at the origin. Okay. Any questions about this? Let's see if I have a better eraser. Slightly better. Okay. So what I want to do now is I want to talk a little bit about Monte Carlo integration. So, in terms of material that you might actually use from this class, this might be your best chance. Okay, if you have not programmed in Mathematica yet, I strongly urge you to write some simple programs. And so here is a Monte Carlo program. And the way it works is the following. I normally do this with a dartboard, but with William's new zero tolerance policy, if you want though, I'm willing to risk it and I'll bring the dartboard later. Alright? Let's imagine we wanted to find, we'll take this beautiful photo of my daughter feeling a Yankee student. Okay? And I wanted to figure out what is the area of her purple shirt. Okay? Here is a really good way to do this. And it's essentially by throwing dots. And if you then think that most of finance is done like this, you can ponder the implications. Alright? Let's assume we can choose a way to throw dots so that every part of this picture is equally likely to be hit. Yes?
Do we know the area of the picture?
So let's say we know the area of the picture. Normally you would try to do this inside a unit square, but for this problem, it's probably better to take something that's not a unit square. So let's say we know the area of this rectangle, and I want to know the area of this sub-region over here. So by throwing the dots uniformly, that means you give me a small square or rectangle, then the probability that I land in that square rectangle is just its relative, it's just the percent of the picture it takes up. So if it takes up 5% of the picture, the probability I land there is 5%. So if I throw the dots a huge number of times, the probability I land in the purple region should be the area of the purple region divided by the total area of the rectangle. And so this becomes a great way to approximate areas. All I need is a very simple test to tell, did I get inside the region or not? So we're going to assume that what we're trying to find the area of is a region where it's easy to say I'm in or I'm out. There are a lot of shapes like that. And again, when you have finance, you will often have 360-dimensional regions that you're going to try to integrate over. But you'll have a very nice set of conditions, you'll have a very nice set of inequalities that will be very fast to check. So now the question becomes, okay, we throw these dots and we see what fraction of the time we hit the purple. What can I do to get a better estimate of the purple region? Increase the number of dots, right? I was expecting someone to say aim for purple. Thank you for being honest, right? The more dots I throw, the better my estimate should be. Is it possible that all the dots are landing in the yellow region? Yes. Is it likely? It is possible that all the air molecules in this room will have all of us in the same boat. We'll go to the corner over there. Alright, so we'll all go together. Is it likely that every air molecule will go to the corner over there? No. And in fact, we can calculate exactly how unlikely this is. And when we get to things like the central limit theorem, we'll be able to quantify this. Now, we don't know the central limit theorem. That's one of the big goals of the course that we're working up to. The proof uses complex analysis, and so since I taught probability last year, and I'm teaching complex analysis this year, we will actually do the proof of the central limit theorem in complex. So if anybody is interested, I will make some additional material available about this. The central limit theorem says if I add a bunch of independent, identically distributed random variables, then it converges to be normally distributed with very nice mean and very nice variance depending on the original random variables. Now we don't know anything like that here, but we do know some results about expected values. What's the expected value of a sum? Some of the expected values. So if each dot, let's say Kayla's shirt has, I don't know, what do you want to say, 8%? Let's say Kayla's purple shirt takes up 8% of the picture. Each dot will have an 8% chance of being in it. And if I throw n dots, I would expect 0.08 n of the dots to land inside the purple region. As the dots are being thrown independently, I can calculate the variance as well. The variance of a sum of independent random variables is what? Variance of a sum of independent random variables. Sum of the variances. So if I do this a lot of times, I will actually understand what my expected value is and what my variance is. This will lead us to things like Chebyshev's inequality, which is a Pohlmann central limit theorem that will allow us to estimate how likely is it. If we estimate the area of Kayla's shirt as 0.073 and we've thrown 1,000,000 dots, how confident are we that this is within a certain tolerance of the answer? Okay? How many of you have ever heard of a poll where people are asked a question? Okay. This would be, who's awake right now. Most polls are poorly done. The reason most polls are poorly done is they ask a bunch of leading questions first, and they don't report the leading questions. They only report the final one. But a big question is, how many people do you have to poll before you have a good sense of the population's preferences? The more people you poll, the more confident you should be, but then you also have to worry about how are you choosing the people? Are you choosing the people randomly? If you're calling people's homes during the day, what's the problem with that? Yeah, people could be at work. And so you've got to be very careful. What if you just go to the beginning of the alphabet? And you say, well, look, I'll just go through the A's.
Certain names might have might be more likely to be from certain.
Yeah, they could be from certain geographic groups that vote certain ways. They could be from the same family, because they'll have the same last name. And maybe you marry somebody who has similar, or maybe you marry somebody who has opposite. So there's a lot of issues in terms of how you would gather this data. So one of the big things we'll be doing later in this course is trying to figure out, based on some observations, what can we say about how confident we are of an outcome. So what I want to do now is I want to show you how well Monte Carlo integration works. So I'm going to ask you all to close your eyes for a minute or two. So everybody close your eyes.
Do you expect to stop them again?
Eventually. I would prefer you not to fall asleep if possible. Keep them closed. I'll tell you when you can open them. Okay, you can open them now. So what I'm going to do is, here is a region. Okay, the red dots are successful hits, the blue dots are misses. Anybody know what region this is?
Unit circle.
It didn't seem to be too hard. So I will pause it. So right now this tells you how many dots I've thrown. I've thrown 205 dots. And I am getting an estimated area of 3.14146. If this were a circle, what would you expect the radius of the circle to be? For the radius?
Oh, the radius.
For the radius?
I think that's the area.
No. I'll change the question. What would you expect the area to be?
It's looking at 3.14.
I know. So you should be expecting.
There's the closing eyes thing.
Right. It is always dangerous. Because of scheduling conflicts, I couldn't take stats from the math department as an undergraduate, and I had to take it from the psych department at 9 a.m. in the room that served as the movie theater. And the professor turned the lights out and put the book on an overhead projector. So here, let's let it play a little bit more. So you can see about 300 dots. Oops, I'll move this so it's not quite blocking.
It seems like it's much denser on the outside.
So this is a fascinating question as to how do things clump and what kind of spaces do you expect. People are horrible random number generators. And so people would tend to have the dots more uniformly distributed than you would get from randomness. In fact, one of the great applications of the Fibonacci numbers is to choose dots in a more uniform manner than choosing dots uniformly. So when you choose dots uniformly, you do get these clusters of misses. And so this is a huge industry right now. What is the best way to uniformly choose points? We don't really want to uniformly choose points. We want the points to have some kind of like lattice structure that's going to fill this out equally. So now we're at around 3,000 points, about 3.15, 3.14. Yeah, at this point it's beginning to look very clear that this is a circle. I will jump to the end. I will try to.
Oh man.
Alright. 8,000 points fell down to 3.12. You know, I should have stopped earlier. I was at 3.14, right? 146. Why did I keep going? You have, when you have small values, you have as good of a chance of being over or being under. Okay? And so it's just a little bit of a fluke that we happen to get really good values at first. How many of you have ever heard of Buffon's needle? So Buffon's needle is one of my favorite problems. When I was an undergraduate at Yale, I was president of the math club because I was a geek, and one of the things I did is I convinced my probability professor to give a talk. And I said, I'll do all the cleanup. All you have to do is come down and give a talk. I said, you'll do the cleanup? Yes. He worked throwing wet spaghetti on the ceiling into the talk. So Buffon's needle is the following. And this is a great probability problem for you to do. Imagine you have a bunch of vertical lines, and they all have the same separation between them, d. And you have little needles. They belong to a guy named Buffon, very good. And they all have length L. Okay? And I will assume L is greater than D. Well, maybe I want to do it the other way around. I'll assume L is less than D. Okay? So I'm going to assume L is less than D. And what I'm going to do is I'm going to throw the needles uniformly. Question? Okay. I'm going to throw the needles uniformly on the grid. And I'm going to keep track of how many times the needle hits the grid. The answer turns out to be the expected value is a rational multiple of pi. It's a really nice calculation. I strongly urge you to try to figure out how to do this. There's lots of different ways you can do this. One way is to say, the center of my needle, well, I have a lot of symmetry here. I have vertical symmetry.
Could you repeat the question?
Sure. I'm going to throw a bunch of needles. Let's say I throw n needles. And I'm going to calculate what's the expected number of crossings of the vertical lines. Okay? With probability 0, I'm perfectly vertical. I can have at most one crossing per stick because L is less than D. And I want to calculate how many crossings do I expect to have. Well, I have an enormous amount of symmetry. I might as well assume the center lies on the x-axis. And so all that really matters is I might as well assume I'm measuring things from, say, this vertical line. I put my center somewhere over here, and I choose an angle theta. And theta can go from 0 all the way up to, I think, pi. And then you can calculate what's the probability that this hits a line. And it's going to be a nice multiple of pi. There's a way to do this calculation without doing any integration. It's a beautiful way of looking at the problem. The reason I'm mentioning this is there are people who've actually done experiments of throwing needles on grids to see how well it works. And so my professor at Yale did this by throwing some spaghetti onto the tiles on the ground. And then he said, let's see if it works as well for wet spaghetti. Not surprisingly, it did not work as well for wet spaghetti, which got stuck on the ceiling. But, you know, I had to take my hat off to him for getting that into his talk. Somebody reported doing this experiment and getting pi to 8 digits accuracy. And what other people noticed is if they had thrown one more needle, no matter what happened, they would have gone down to 3 digits of accuracy. What they had done is they had deliberately fabricated an experiment by looking at a really good rational approximation for pi and pretending they threw that many needles with that many successes. This is an extremely important point that I really want to emphasize. This is why I'm taking a couple of minutes to go over this now. Be skeptical when people present you with data and results. It is very easy to mislead. And so here was a really great thing. You know, wow, this is 8 digits accuracy. What would have happened if they had thrown one more? Either way, 3 digits accuracy. Now again, is that a proof that this person was lying? No, but I'm very suspicious. The other thing is, whenever you have a problem, you want to ask yourself, what can you say about the answer? Are you surprised that pi is coming into play for the answer here? So is anybody surprised that we're getting a pi as the answer? Okay, is anybody not surprised? So why are you not surprised that there's a pi?
You have an angle thing.
We have an angle. So maybe the fact that we have some kind of angular freedom is going to lead to a pi coming into the answer. The best way to do this, and I'm going to just sketch the argument here, if anybody wants more details, let me know, is to use one of my favorite techniques, which is...
Adding by 1?
Ooh, no.
Program.
Wait. What did you say?
Oh, adding by 0.
I mean, I'd love to be able to add by 1, but I can't. Nope, it's not adding by 0 or 1 or multiplying by 0 or 1.
Computer generated.
I'm sorry?
Do an example on the computer.
Nope.
Proof by story?
Nope. Linearity of expectation. You could actually solve this with linear. What you do is you basically say, let's take a bunch of sticks of the same length, drawn hopefully better. And if you do a bunch of small sticks of the same length, what's going to happen is you'll get all possible angles. And imagine you've just put them together as a circle, and you throw down the circle, and you choose the radius of the circle to be exactly d. So it's going to always have two intersections. So it's a really nice exercise. You can solve this using linearity of expectation. If you've ever heard of the mathematician Erdős, Paul Erdős said you do not need to believe in God to be a mathematician, but you do need to believe in the book. Okay? So according to Erdős, God has a book. And in the book are the best proofs of the various results in the world. So a couple of colleagues of Erdős actually wrote a book called Proofs from the Book. Chapter 1 is 6 proofs of the infinitude of primes. One of the chapters is on Buffon's needle and throwing down needles into a circle and solving this without doing any integration. So the highest praise Erdős could give somebody is, this is a proof from the book. It's beautiful, it's elegant. Lots of good stuff here. All right, let me do one more region. So if you can close your eyes for one more minute. Okay. All right, what region? Any thoughts? Rectangle? Rectangle looks like a mostly good guess. Except this blue point here, I think that blue point kills the rectangle.
Ellipse.
An ellipse, right? If I did a circle, what's the smallest thing I can move it to? Alright, so here, I've done only 904 points, and I'm getting 1.65. Does this look reasonable? Who knows the area formula for an ellipse? We have an issue now. Okay, if you know the area formula of the ellipse, you are no longer allowed to play today's game. Okay? So let's try to figure out what do we have. If looking at this picture, you've got 904 data points. Let's let it run a little bit longer. We'll let it run all the way to the end. Let's speed it up. All right. So we've now, it doesn't stop. That's how it goes.
It seems much more densely now.
So again, a fascinating question is these clumps of whiteness. If you don't have these clumps of whiteness, it's not truly uniformly distributed. And so in fact, a lot of my research is related to stuff like this, and trying to understand the distribution of these hits. If you had to guess, you need the equation of an ellipse. What would you say the equation of this ellipse is?
Pi over 4. Or pi over 2.
The equation?
The equation of an ellipse. Okay, everyone just wanted to jump to the areas. Oh, I just realized this probably was not on the simulation. Oh well, that's the simulation. Okay. What would you guess? You need for x over a squared plus y over b squared is less than or equal to 1. Looking at this, what would you guess is a? What would you guess is b? So 0.51.
A is
0.51.
A is 1.
A is 1. And b
Is a half.
is a half. What do you guess for the area? So 1.586. Pi over 2. I believe the talk in today's colloquium is on summing the series 1 over n squared and getting pi squared over 6. Right? What I want to do is I want us to be a little bit of an experimentalist today, without having to use our money for expensive equipment. Right? You see pi over 2. How would you rewrite this in terms of the parameters that we have here? I want the area of an ellipse, and I want it in terms of the parameters that I have. What would you guess?
Pi divided by a divided by b.
Okay, it would be pi what?
Pi over a divided by b.
Okay, a divided by b. Okay, that's one conjecture. Other conjectures.
B pi over A.
b pi over a, which is the same.
Yeah, but where do you do that?
Now you owe me a real conjecture.
Okay.
So we'll write this as pi b over a.
There we go.
Yes.
Pi times A times B.
Pi times a times b. And I'll write down 1. Okay? So at least one of these you should be laughing uproariously over. What I want to do is I want to talk about how do you look at an equation and get a sense of what the answer is without actually doing the calculation. I claim when you look at these, only one of them is a reasonable candidate.
Well, it's symmetric, sort of. I mean, A and B have to be the same.
Good. So whatever answer we have, we shouldn't be able to tell the difference between A and B. Right? So I should correct mine to that. Now at least it's competitive. This is extremely important. This is probably more important than anything else you're going to be doing in class today. Is how do you look at a complicated equation, how do you look at data, and get a sense of what you should conjecture. Did we prove the Pythagorean formula at the start of the semester? No. Okay. If there's time at the end of class today, we'll prove the Pythagorean formula. You want to do a kind of unit analysis. If I have an ellipse, let's think of A and B as in meters. So what should the units of the area be? Meters squared. So if we look at the first thing, pi b over a, the meters in b and a cancel, and this would be unitless. This would have units of meters squared. And this would have... Oh, I have no idea what that one would be.
Meters to the A times B.
Meters to the meters.
Yeah. Okay. So, gone, maybe. Are there any special ellipses that you understand well? The circle. Right? So in the circle, A equals B equals R. Does this reduce to something that you understand for a circle? Yes. This is pi r squared if A equals B equals R. So this is a great way for me to give you a little talk on the change of variable formula. So you can actually get the area of an ellipse in one line if you know the area of the circle. Unfortunately, you cannot get the perimeter of the ellipse in one line if you know the perimeter of the circle. Perimeter is very hard to work with. Area is very easy. So, change of variable formula. So this is something that you've all taken in Math 105, 106. You all know really well, so I don't have to spend too much time on it. If for some chance that is not the case, talk to me or look at the appendix on the book on the change of variable formula. I want to calculate the integral over minus a, I'll do it this way, x over a squared plus y over b squared less than equal to 1 of 1 dx dy. I want to calculate the area over this region. I could set up the bounds and have x go from minus a to a, and then y is going to go from 1 minus x over a squared square root times b. I could write down those bounds. I don't want to write down those bounds. I don't want to do integrals involving square roots. If you want to, by all means, this is still a free country. Please do so, but don't take me with you. Okay? If you could change variables, how would you change variables? I want two new variables, u and v. What would be a really good choice for you that will make the ellipse look like a nice region? So I've got x over a squared plus y over b squared is less than equal to 1.
X over A.
X over a. And v would be y over b. This would then give us du is dx over a, dv is dy over b. So this integral becomes the same as the integral u squared plus v squared less than equal to 1. But now what does dx dy become? Well, dx dy is just ab, oops, yep, du dv. So now I'm just integrating the function AB over the unit circle. What's the area of the unit circle? Sorry? What's the radius of the unit circle? It's okay, Chris. For the record, this is why he didn't get the business card when he visited. What's the radius of the unit circle? Years ago, my brother once asked my father, "What's Frank Ming's last name?" So, what's the area of the unit circle? Pi. So we just get pi AB. And there's the proof of the conjecture. If I gave you x over a squared plus y over b squared plus z over c squared is less than or equal to 1, would that be a problem? If I gave you the ellipsoid? No. And you get the volume of the ellipsoid is 4/3 pi ABC. So the change of variable formula is a wonderful way to go. Now what was nice here is I did not have to explicitly write down the range of integration. So how many of you are willing to admit that you've seen the change of variable formula at some point in your career? How many of you are willing to admit that you don't like using the change of variable formula? Not as much as I was expecting. One of the hardest parts of the change of variable formula is writing down what do the regions become. In this case, the region becomes very nice. We're going from an ellipse to a circle. I don't need to write things down explicitly. If I wanted to, I could write u goes from minus 1 to 1, v goes from minus square root of 1 minus u squared to the square root of 1 minus u squared of ab dv du. I could do it like that if I wanted to. Okay. So what I like about this problem is the Monte Carlo simulation suggested what the answer should be. And then we had some parameters at our disposal. In the real world, what you would do is you would do these simulations for a bunch of different ellipses. And you would record the values for A and B, and then you would try to figure out, given this data, what's the most likely formula. So one of my favorite topics later in the semester is the method of least squares, which will talk about how to go from various observations to best fit lines. So proof of Pythagoras. So we really haven't proved Pythagoras this semester? Okay. Only one US president is credited with a proof of the Pythagorean theorem.
Garfield?
Yeah.
Garfield. Right? Who died on his way to what? Be more specific. I think it was his 25th reunion. Okay? But Garfield is the only president credited with a proof of the Pythagorean theorem. As much as I like Garfield, I have to admit his proof is highly derivative of the standard trapezoidal proof. But hey, he got it through, he has credit for it. I'm going to show you my favorite proof of Pythagoras. I will show you first the proof I've used the most, until maybe about a few years ago. So A, B, A, B, A, B, A, B. This is not my favorite proof. Okay? I have 4 triangles. The area of the triangle is 1/2 base times the height. So I have 4 times 1/2 AB. This is 90. With a little bit of work, you can see all of these angles are 90. So this is a square. But these pieces completely fill the square of side A plus B. So this has to be A plus B squared. And when you experience together, I have a 2AB, 2AB cancels, and you get C squared is A squared plus B squared. So for a long time, this was my favorite proof of Pythagoras because it was easy to remember. I want to show you a better one. I want to show you dimensional analysis. This is one of the big takeaways for the course. If you have something that you're studying, are there natural units you can use to get a sense of what's going on? What can you tell me about the area of a triangle if the sides are in meters?
The area is in meters.
The area is in meters squared. That's essentially the proof. So here's my triangle. Here's A, here's B, here's C, here's theta. I claim that the area is equal to f of theta times c squared for some f of theta. If I double C, using corresponding parts of congruent triangles are congruent, if I double C, I double the base, I double the height, the area increases by a factor of 4. If I triple C, I triple the base and height, the area increases by a factor of 9. The area of a right triangle is proportional to the hypotenuse squared. I can figure out what f of theta is. It's going to involve, sine of theta and cosine theta, and probably a 1/2. Okay? I'm not going to use trig. All I'm going to say is, for each theta, there is some number such that the area of the triangle is f of theta c squared. Everybody comfortable with this? Okay. How many of you remember your geometry proofs? So if you do not like having me as an instructor this semester, this is what caused me to stay in mathematics. I loved geometry, where the rules of the game were clearly given. Here's the axioms, here's the definitions, here's the laws of logic, statement, reason, proofs. You can't get anything by you. When you do geometry proofs, typically you have to add what? Remember this, when you're doing geometry proofs, you typically have to add something to the picture. You add an auxiliary line. And usually when you draw the line, it's, yes. Right? So the question is, what is a good line to draw for this problem? Well, we're trying to do things involving right angles and right triangles. Can anybody give me a line that will give me more right angles?
I don't remember what it's called. From the corner of AB perpendicular to C.
That's exactly what it's called. Although some older books call altitude, I think.
Okay.
But they're equivalent. So if I do this, I have little bitty triangle 1, medium triangle 2, and big triangle 3. If this is theta, this is 90, this angle here is 90 minus theta. What's this angle over here? Theta. So I have a little triangle, and it has an angle of theta. What's the area of the little triangle? F of theta times a squared, because its hypotenuse is a. What about the medium triangle? Does it have an angle theta? What's its hypotenuse? Its hypotenuse is? Some of you see the punchline coming. And since the two triangles fit together so nicely, it's f of theta. Okay, now what would everybody like to do? Okay, are you allowed to do that? I'm sorry? It's all the same theta. So can we just cancel and get a squared plus b squared equals c squared?
What if f of theta is 0?
I'm sorry?
Could f of theta be 0?
That's the only issue we have, is if the f of theta is 0. What would it mean for f of theta to be 0? The triangle would have 0 area. We don't have a triangle, right? So again, we are not in an engineering class, we're not in a physics class, we're definitely not in an economics class. Before we do something, we have to check and see, can we justify? The issue here is, can we justify canceling? Yes. F of theta is not 0. And so because f of theta is not 0, we can cancel. Alright, so we got to do a lot of good stuff today. We got to see the CDF method. And if you think about it, there is a connection between the CDF method and the Monte Carlo integration leading to this. It's all the change of variable formula. The CDF method is change of variable in 1 dimension. What I was showing you here is change of variable in 2 dimensions. It's actually a unified lecture today. Okay? There is a lot of interest about which dots and which areas are missed. And then over here, this whole unit on dimensional analysis, which is a great thing to really soak in. All right, if you have not picked up your